we'll discuss. So the material we discuss in this lecture is directly taken from Pulchinski chapter 4. It's the no course here. In the next lecture, we will complete our discussion of the material in Pulchinski chapter 5, discussing various. We had this lovely formula for scattering amplitudes in bosonic string theory, but there were many questions about that formula that we left unanswered. You know, does it remain invariant if you choose different vertex operators to be fixed and integrated over? Is it BRST invariant? That was not a question we could address when we wrote down the scattering formula, because we didn't know what the BRST symmetry was. But now we formulate an equivalent question and answer. So, okay, so these next two lectures will the plans to clean up a formal discussion of string amplitudes. After that, we'll start actually trying to revisit string theory. We'll try to calculate scattering amplitudes with it. We'll have fun. Okay, so let's continue. So let me remind you what we discussed last time. We had this general discussion about Faddeev-Popov gauge fixing, and how whenever you Faddeev-Popov gauge fix a symmetry, there is at least formally, you know, if, at the classical level, if you know quantum anomalies, there is a fermionic symmetry naturally defined. There's a fermionic symmetry naturally defined associated with the gauge fixed action. So let me very briefly, in 2 minutes, remind you of that discussion since it's been a month-long break. You remember that the fields in we said suppose you get fields which are phi I. That there's a gauge symmetry which is generated by delta alpha. Delta alpha acts on phi I to any function of phi I. And this delta alpha weight the symmetry delta alpha delta beta is equal to f alpha beta gamma delta. Gamma is f alpha beta the structure constants of the theory. And we choose to quantize the theory by fixing the gauge conditions fa of phi equal to 0. Okay? When the Faddeev-Popov procedure gave us an action that was S was equal to S yang, I call it yang, but it's just the gauge invariant action of phi I. Okay? Plus the term that was the delta function, and we get my plus minuses, right? Minus the delta function associated with gauge fixing, plus the term that was the Faddeev-Popov determinant. Here that's something else. Signs, right? So the term associated with Faddeev-Popov determinant was what? There was the determinant was two indices for which gauge fixing condition and what variation of the gauge transformations, right? So there's a BAC alpha, each of these are fermionic, and then delta alpha. This is a very nice compact general form of the action for the gauge fixed Lagrange. Okay? And then we noticed that this action had the following symmetry. That had a symmetry under the following transformation. Under delta phi I was a gauge transformation generated by the gauge parameter C alpha. C alpha delta alpha phi I. Okay, and if we stick to Pulchinski's convention, there's a minus I here. There's also an overall anti-commuting parameter, minus I absolute. Okay, then the change in BA was 0. The change in little BA was equal to epsilon times BA. Sign right, yes. And the change in C alpha was equal to I by 2. F alpha beta gamma C beta C. Yeah. Okay. Good. Okay. And under this transformation, we saw many things. We firstly checked that this transformation was nilpotent, so that the generator of this transformation squared to 0. We checked that by checking the action and by just doing the action twice in any of these fields. We checked some explicitly and others with F2 do the next exercise. Okay, now the next thing that we checked was that this action here took very simple form. It could be written as SYM of phi I plus Q acting on BAFA. Probably with a minus. Well, with some conventions with a certain minus sign. Okay? And the important point about this action was that the details of the gauge fixing function entered the action in a Q exact fashion. That is, the action changed by Q acting on something. If we rewrote this in operator language, we canonically quantized the system and wrote down an operator that generates this Q symmetry, then that Q acting on this would become the anti-commutator of Q with BAFA. Okay? Now, we wanted to deal with, you see, the question that we asked on BRST gauge fixing was the following. We said, well, suppose we were dealing with the gauge theory, we want to know what the Hilbert space associated with that gauge theory was. Okay? So, if you ask this question from first principles, there are ways to answer it. You take the path integral of the gauge theory, slice it, and see what Hilbert space this gives you a trace of. You can answer this question honestly. However, in doing perturbative calculations, we introduce all this other machinery, right? All these other costs and so on. Now, one could take this action at face value and just canonically quantize this action. Consider the path integral, slice the path integral of this action. Okay? Associate a Hilbert space with it. This is clearly sort of a larger Hilbert space than the Hilbert space of the original theorem. For instance, there are more fields, these ghosts. So the question was, what is the connection between these two Hilbert spaces? So really the question was, is this BRST method merely a trick for computing path integrals? Which it clearly is. That's how we introduced it. Or can we do better? Can we give a nicer physical interpretation of the BRST method? Can we also give a Hilbert space interpretation of the path integral that we get using BRST techniques? That's the question we asked. Now there was no pressing logical reason that the answer had to be yes. But in fact it turns out to be yes. Okay? And so what we want to do is to identify a special subspace of the Hilbert space of BRST quantized theory and to make a candidate identification of this subspace as the physical Hilbert space. The Hilbert space that we would have got had we honestly done the canonical quantization of our original theory. Okay? So that's the question we're asking. Now, we don't know a priori how to answer this question, but we do know that the answer to this question must have a certain property. Okay? Matrix elements, time evolution matrix elements of honest physical states, honest states of the Hilbert space, must be independent of our choice of gauge fixing. Okay? So if we've done this all correctly, and we presume we have, this must be true. However, can you see that the path integral and the Hamiltonian of the theory appear to depend on the gauge fixing parameter, on the choice of the gauge fixing parameter, but they appear to depend on it only through this Hamiltonian function. So if I change the gauge fixing parameter a little bit, I change the Hamiltonian, but the anti-commutator of Q will be a delta F. Okay? So if we choose our physical states, we choose to restrict attention to those states that are annihilated by Q. You remember we also discussed the Q as a Hermitian operator, so it acts both on the left and the right. Okay, so if we choose to restrict attention to those states chi, which are annihilated by Q, then such matrix elements for those states are invariant under a change in the gauge fixing function. Because the change in such a matrix element is simply, the change in this is simply chi A, Q, B, A, delta F, A, chi B, and this term is 0 because either Q annihilates chi A by hitting from the left or from the right. Was this clear? Okay? Similarly, we might be interested in more than just matrix elements, we might be interested in operator insertions, yeah? But once again, if we choose the operators commute, or respectively commute or anti-commute with Q, depending on whether they're fermionic or bosonic, then the same conclusion goes through. Right? this thing just goes through all the operators and annihilates the vacuum, the physical state either on the left or on the right. Okay? So we will also choose to restrict attention to those operators which are Q invariant in the sense of computation, or anti-computation. Okay? With this restricted view, these states, these matrix elements of these states, and matrix elements of these operators in these states, okay, are invariant under change in gauge fixing condition. Okay? So our physical Hilbert space can at most be, the largest space it could be is the space of states that are annihilated by Q, and the largest space of physical operators that could be is the set of operators that commute with Q. There could be further restrictions that don't come out of this simple condition, but this is a necessary condition. Otherwise, the theory would make sense. Okay? So that was the first thing. We restricted attention to states that were annihilated by Q. So Q on psi was equal to 0. That was our first condition. Now, the next thing we noticed was that suppose you had any state chi that was equal to Q of some zeta, some other state zeta. Then the inner product of chi with any physical state, inner product of chi with psi, which is the same thing as zeta Q psi, was equal to 0 as long as psi was physical, because Q annihilates psi, Q is commission. Okay? So, because Q is commission and Q annihilates psi. Okay, so in particular, since Q squared is 0, any state of this form, any state chi of this form is physical, in the sense that it's annihilated by Q. However, it's orthogonal to all physical states, all other physical states, including itself. Okay? So, the matrix elements between any such state and any other physical state is 0. And that continues to be true for matrix elements including operator insertions as long as the operators commute with Q. Okay? Therefore, any two states that differ by a multiple of such a state have all matrix elements equal. Okay? So all probabilities of doing, starting with something in one state, ending with something in another state are identical for all these states. So clearly these states should be thought of as describing the same physical system. Because you can't, they're physically indistinguishable. Okay? So our final prescription was as follows. The true Hilbert space of the theory is the equivalent, is made up of equivalence classes. First we define this sets of physical Hilbert space, the space of states that was annihilated by Q. And then we looked at equivalence classes where states were considered equivalent if they differed by a multiple of Q acting on some other state. And we identified as a trial, we identified our Hilbert space with this equivalence, this set of equivalence classes, which has a name mathematicians like to call this Q cohomology. Okay? So this was our trial identification for the physical Hilbert space of our system. Okay? And in the quantization of the free particle and inherited string theory, we argued that we needed one further condition. That in addition to states being BRST invariant, we also required these states to be annihilated by the zero mode of B0. You remember when we did the free particle, we got twice the right answer, and we killed the wrong part by asking for the states to be annihilated by the zero mode of B0. Okay? Great. So this is what I wanted to remind you of about our general discussion of BRST invariance. Any questions or comments about this? Great. Now, then the next thing we did was to discuss BRST invariance of the world sheet of the string. So, we managed to produce, we sort of went ahead and implemented this general procedure on the world sheet of the string, and we managed to produce this nice BRST current, which was equal to C times T, T matter, plus, plus B. It was half C times T cos, but the more useful way of writing it was BC del C. And And then plus the total derivative term that we added in order to make the current tensor. 3 by 2 del squared C. Okay, we have this nice BRST current which generated BRST transformations in the sense that the OP between this current and all the fields had poles and the residue of the poles, which gives the transformation of that field under the symmetry operation generated by Q was the correct thing. Okay, and we computed many things about this BRST current. We talked about how this BRST current in OP with itself had zero residue of pole only when D was equal to 26. But the OP of this BRST current itself is related to the QQ anticommutator. So the fact that Q squares to 0, while classically always true, was quantum mechanically true only when D equals 26 at the critical dimension. So from the BRST point of view, this was from the BRST Hilbert space point of view, this was the special thing of the critical dimension. That Q squares to 0. By the way, Q is always a symmetry of the theory in every dimension. Always generated a symmetry of the theory in every dimension. You can see that just by the fact that the BRST current was analytic. Therefore, was conserved. Okay, Jz was analytic, Jz bar was analytic. Therefore, del Z bar of Jz plus del Z of Jz bar was 0. That which is automatic. However, the thing that was special of the critical dimension was that Q squared to 0. Okay, we also worked out the OPs between the BRST current and all the other fields in the theory. The one that will be of relevance to what I have to say today, I'll rewrite. So J BRST of Z with B of 0 had many terms, but the pole piece here was Tm plus Tg on Z, where Tg was the energy momentum tensor of the closed part of the set. Okay, and this in particular implied that Q with Bm was equal to Lm. Okay, where Lm was the Fourier modes of the full stretch sets, the matter plus post. And in particular, the thing that we will really use today is that Q with B0 is equal to L. Okay, where L0 is the full zeroth order Fourier mode of the ghost stretch sets. Okay, so this we're going to use heavily in a little bit. Questions or comments before this? Questions or comments before this? I'll let you proceed. Okay, great. Now, I just want to remind you about the structure of L0. So, what was L0? So, L0 included the zero mode part. So, there was a part we'll get coefficients straight into it, but schematically at the moment there was a part that was alpha prime p squared, actually it was 4, but okay, alpha prime p squared, plus there was the number operator associated with x oscillator, so let's call that nx. So this thing was sum over m alpha mu minus m alpha mu m is equal to 1 to infinity, and this is all mu. Okay, but and remember that these alphas have their commutation relation such that they commuted to m. So each of these modes, the mth alpha mode has energy m. Okay. And plus there were number operators for the C modes and number operators for the B modes. Okay, so analogous definitions, with the C modes being a B plus M with a C minus M. Okay, and and the B modes being a B minus M with a C plus M, because C plus M destroys a B minus M. And then it creates it. Okay, so there was an analogous term, a piece like this, but there was also a normal ordering constant. Okay, now the normal ordering constant for the matter part of the of L0 was 0. We worked this out in detail, right? But if you remember when we were just discussing the BC ghost system, we also discussed what the normal ordering constant was for the stress tensor of the BC ghost system. And you remember we got the answer lambda into 1 minus lambda divided by 2. Okay? Now, in this system, in the BC system we're talking about now, lambda is equal to 2. So this thing is 2 into 1 minus 2 divided by 2, so that's equal to minus 1. So when you rewrote L0 in terms of oscillators, you took these oscillators and you oscillator normal ordered them. Remember, this is different from conformal normal ordered. That was the origin of this normal ordering constant. It didn't make a difference for the matter part, except for zero modes where you have to think a little bit. But for the ghosts, it made a difference. Again, basically because these had funny weights. Okay, so for the ghosts, it made a difference. And if you take L0 and rewrite it in terms of oscillators, which are normal order, so in terms of these number operators plus constant, there's an additional minus 1. Okay, which comes from the zero mode of this business. You remember we had two ways of deriving this. Do people remember this normal ordering constant? We had two ways of deriving it. First one was just looking at the difference between conformal normal ordering, where we define the L0 operator, and operator normal ordering, using that to directly compute the difference. The second way, which was easier but less conceptual, was to use the fact that L0 is a commutator L1 and L minus 1. L1 and L minus 1 had no normal ordering immediately. Okay, so those were completely well defined. So if you use that to define L0, you got the right answer with the normal ordering. Both ways give the same answer. This course has been a little staccato, so you may have forgotten this, but I'll ask you to go back to your notes and look up. Okay, you've forgotten this. This is minus 1 very important. Okay, so why was I saying all of this? Why was I saying all of this? I was saying all of this because, you see, you remember that we started more or less this lecture by saying that we're going to impose the condition B0 on psi is equal to 0 and Q on psi is equal to 0. But we also know that the anti-commutator of Q would be 0 is L0. Okay? So it follows that if both these conditions are imposed, it follows that we also want to impose the condition L0 on psi. These two imply L0. But remember, this is the full L0, including the normal ordering constant. Okay? So, now in this lecture, what we are going to try to do, so this of course is this condition, L0 on psi is equal to 0, is the mass shell condition, or string theory. Right? Because this tells you that the mass squared in units of 4 divided by alpha prime. So this condition tells you that the mass squared is equal to 4 divided by alpha prime, and then there's minus 1 plus oscillator number. When in the closed strips, we get such a condition from both the left and right, so level matching conditions. Is this clear? Okay? So in this lecture, what we're going to try to do in more detail is to understand Q cohomology on the worldsheet of the strip. But we're going to restrict our attention to those states that obey Q cohomology that obey B0 on psi is equal to 0 and L0 on psi is equal to 0. And this is a consistent subset of Q cohomology because of the following combination relations. Because Q with B0 is equal to L0 and Q with L0 is equal to 0. Q is a conserved charge commutes with the Hamilton. Okay? Because these two relations are true, the restriction to states that are annihilated by B0 and L0 is self-consistent. You start with the state that's annihilated by B0 and L0, you act with Q on it, it will continue to be annihilated by B0 and L0 because these two conditions, because L0 is 0 on the states of the consideration. Okay? So we don't need to, we can simplify a problem by instead of looking at all the states, looking at those states that are annihilated by B0 and satisfy the Marshall conditions. Okay? So within this subset curve we wish to examine Q cohomology. So I'm first going to give you a very formal argument of this no-host theorem, and then we look at it in examples to try to understand it. Okay. So the final thing, the thing that we're reaching to prove, what we want to show is that this Q cohomology with this additional condition B0 states equals 0 is the right answer. Now what is the right answer? Now the right answer is what we got to in the second or third lecture of this course, namely the spectrum that came out of the line-cone quantization of the bosonic string. Okay? The right answer is a bunch of particles, one associated with every oscillation of the 24 transverse directions. So I want to, of course, the inverse space that we see here has much more in it. It has 28 different kinds of oscillators. B oscillators, C oscillators, and the 26X oscillators. So we have to get rid of 4 kinds of oscillators somehow or the other. And the claim is that Q cohomology does this. That the answer to Q cohomology is precisely one-to-one correspondence with the correct excitations, these transverse excitations of the string. So we want to prove this. So let's see how do we go about it. Okay, is the goal clear? Fine. So the argument I'm going to start with is formal, and you may not see exactly where we're going to start with, but please hang on and have patience, and you'll see where we reach by the end. Okay. So the first thing I do, and this seems totally removed, to start with, we want to get correspondence with the transverse degrees of freedom. So we should, out of these 26 degrees of freedom, time is special, of course. But in addition, we choose one other spatial direction, like we did for line-cone quantization, and isolate it. So let's define alpha plus to be alpha 0 plus alpha 1 by square root. I'm making this definition for oscillators, so there's an M here. M runs from minus infinity to infinity. Okay? And let's also define alpha minus. Sorry, this is alpha 0 plus alpha. Yeah, so this is the time direction, this is the one special spatial direction. You might want to call it alpha 25, but let's call it 1 just to save it. Okay? And let's define alpha minus M is equal to alpha 0m minus alpha 1m divided by square root. Okay? Now let's try to figure out what the combination relations between these alpha plus and alpha minus. So first tell me where is alpha m plus alpha n plus. Somebody tell me where we get. 0, exactly. So there are 2 ways of seeing it. One is directly. The second way is just to write on the covariant forms of commutation relations. The covariant forms of commutation relations had G mu nu on the right hand side, but there's no G plus plus. G plus plus is 0. Okay? Or more directly, we get something when m is equal to when this m is equal to minus n. We get something from the 0 term, but we get the opposite thing. We get something from the 0 term, but the opposite thing from the 1 term. Because the commutation relations involve alpha m0, alpha n0 is equal to delta m minus n times the factor of m times g00. And g00 and g11 are negatives of each other. Okay? So this thing is equal to alpha minus m, alpha n minus is equal to 0. However, alpha plus m and alpha minus n, that is not equal to 0. It's the fact that we have a g plus minus on the right hand side. And let's compute it from, let's write this as m delta m minus n. And from the 0 terms we would get a minus sign. From the 1 terms we also get a minus sign. So that's a minus. Okay, you get a factor of 2, and then this 2 square root 2 is in the denominator, cancel that factor of 2. Okay, so we've got this nice commutation relation. For these alpha pluses and alpha minuses. Okay, now we're going to define an operator which we call NLC, the number of light cone oscillators. And this operator is defined as 1 over m, 1 over m, sum over m, 1 over m, and order it alpha plus minus m, alpha plus minus m, alpha minus m, and m is summed, m is equal to minus infinity to infinity, but not equal to 0. Okay, it's summed over all integer, non-zero integer values. Okay? Now, before proceeding, let's give a physical interpretation to this NLC operator. I want to claim that this NLC operator, acting on a state, counts the number of minus excitations minus the number of plus excitations in that state. Okay? Let's see this at work in a simple example. Suppose psi was equal to alpha minus of minus k, with k a positive number, on 0. Okay, so what term in this state would be activated? So the only term in this operator that would be activated was when alpha plus came with a plus k. Okay? That term would have alpha plus. Okay, let's do it carefully. So what we want to do is to compute NLC on alpha minus of minus k on 0. Okay? Now, I'm claiming that the only term, you see, this is a sum of terms with one index plus and one index minus. So the plus index would annihilate the vacuum unless it is killed by a commutator going through here. So the only term that can contribute is when something that can click with this, which is alpha plus of k, alpha minus of minus k, and then we want to divide this by minus k. Right? Because we're supposed to divide by the negative of the index and the plus. Okay? This thing acting on alpha minus k. Now, alpha plus k with alpha minus k, according to this formula, gives you a minus k, because this commutator has a minus. Okay? So, we take this through here, that makes no difference. We take this through here, and I get the vacuum up to the factor of commutator. The commutator has minus k. We get minus k divided by minus k, then it's alpha minus minus k. Okay? On 0. So this state had eigenvalue 1 under NLC. Is that clear? Here Similarly, if you have many factors of alpha minus k1, alpha minus k2, so on, you get a factor of 1 for each of these guys. Okay? Now, if you check that if instead you had an alpha plus k, you would get a factor of minus 1. Okay? The signs work out like that. Is that plausible, or would you feel too uncomfortable and you want me to check? Okay, it's okay. Great. So this operator, what it does is count the number of minus oscillators minus the number of plus oscillators. Okay. Now, very good. Now this operator is almost, is almost a symmetry of the theory. It's almost, okay, though we won't use this and I won't try to justify it in any detail, it's almost the generator of Lorentz transformations in the plus minus boost direction. It's not quite that, because, would have been that had we also included contribution to 0 volts. But what we've got here is something that's almost a symmetric generator of the theory, except that it's not quite because we're not including contributions from 0 volts. Okay? So what do I mean by that? So let me look at a particular operator. The operator that will be of interest to me is Q. Okay? So let me look at the operator Q, and let me look at what the value of NLC is on the various terms of Q. Okay? So let's see. So Q, of course, has part that is pure host. That has 0 NLC, of course, because there's no plus minus oscillators. So the interesting part is the part that came from the integral of C del x del x, with C times stress constant. Now, what is C del x del x in oscillator language? In oscillator language, that is C, let's say, minus M minus K alpha M alpha K summed over all alpha mu summed over all M and K. Okay? Actually, even the factors are correct here, because the expansion of C, del x is simply expanded in terms of alpha. It has this usually. So in these factors, this formula is really just correct. Okay. So now let's look at this formula. Of course, any term where these mu indices of the transverse dimensions is NLC equals 0. We don't care about those. So what we care about instead are the terms in which this is plus minus. Okay. Now, there are various kinds of terms. Sorry. Plus minus. Yes, we're summing over all of them. Yeah. That's true. Okay. So now there are terms. So there are various cases. One case is that M is positive and K is positive. These are modes that destroy a plus oscillator and destroy a minus oscillator. So for such terms, NLC is 0. Okay? There are other terms in which M is positive but K is negative. Now, K being negative creates a minus oscillator, but M being positive destroys a minus oscillator. So NLC is just 0. Do you see this? So let's do the two cases again. Suppose both were positive, then both are destruction operators. But remember that a positive value on alpha minus is a destruction operator for alpha plus, for a plus oscillator.
I'm just worried about factors of number line here. So that wouldn't matter.
You see, we've got the physical interpretation of this thing. It actually counts the number of oscillators with no factors. Okay. Remember, we got these factors nicely cancelled. So NLC is just the operator that counts the number of oscillators. Number of minus oscillators minus number of plus oscillators. No other factors. Okay? So, suppose both are positive, then this is a destruction act on some state. Either it gives you 0 or it destroys a positive oscillator. This is a destruction for a negative oscillator. So it reduces the number of positive oscillators by 1, reduces the number of negative oscillators by 1, so that NLC equals 0. That's clear. You might think, oh, what about if this guy was negative and this guy was positive? If this guy was negative, it creates a minus oscillator. But this guy being positive destroys a minus oscillator. So once again, NLC is 0.
Okay, so the statement is that the NLC commutes to this.
Wait, hang on. Yes, that's right. So that it's eigenvalue under commutation of this operator. Terms of this operator where everything is either positive or negative is 0. However, that doesn't exhaust it, because remember we defined our NLC to exclude 0 roots. So there are terms here in which one of these is 0. Okay? So, suppose we look at the term where this guy is 0. If this guy is positive, then it destroys a minus oscillator. If this guy is negative, it creates a plus oscillator. In either case, it has NLC equals minus 1. On the other hand, if this index was 0, we will get NLC equals plus 1. Because we have creation operators for minus oscillators or destruction operators for plus oscillators. Okay? So we come to the conclusion that we can write Q is equal to Q minus 1 plus Q0 plus Q plus 1. Where the index reflects the charge of this operator under computation with NLC. Okay? Now Q0 is most of the operator. It contains all the part that is pure burst, contains all the part that has transverse oscillators, contains all the part that is bilinear in oscillators of plus and minus. However, Q1 and Q minus 1 contains that small part of Q that has a 0 mode contribution from either plus or minus. And we just decided that Q1 could be written as sum over C minus M alpha plus 0 alpha minus M. M equals minus infinity to infinity, now equal to 0. No, yeah, Q1 is equal to this. Is this clear? Okay? Great. Now, the next thing we look at is, we're going to be acting as Q on states. So we choose our states to be in a basis such that they're in eigenstates of the 0 mode momentum operators. So that the wave functions are at e to the power ex. Okay? In that case, alpha 0 plus acting on a state is simply k plus, the plus component of the momentum. Because remember, alpha 0 is the momentum operator up to an overall normalization. Okay? So we won't worry about the overall normalization. Polchinski has it, it's a square root of 2 alpha prime, but plays no role, so let's not worry about it. So Q1 up to an overall normalization is k plus sum over C minus M alpha minus M, M not equal to 0. Acting on a state which has momentum, this has some momentum k plus. Okay. Now, you see, let's take the equation q squared is equal to 0. This equation is q minus 1 plus q0 plus q1, the whole thing squared is equal to 0. And we can decompose this equation into those operators that have all possible allowed values of NLC. Okay? If an operator is 0, its projection onto any given eigenbasis is 0, 0, 0, 0. So the parts of the operator that have, what are the allowed values? The allowed values in q squared are NLC equals minus 2, NLC equals 0, and NLC equals plus 2. The part that's minus 2 is q minus 1 squared. The part that's plus 2 is q1 squared. The part that's 0 is something more complicated. Okay? But each of these must independently be 0. Okay, because the operator is 0. It's like you've got a state 0. You look at its basis elements in some basis. All these coefficients must be 0. Okay? So each of these is independently 0, and in particular q1 squared is equal to 0. So we could consider, instead of studying the complicated problem of studying BRST cohomology, we could first do what at first sounds like a warm-up, that is study the problem of computing q1 cohomology. It's a well-defined question because q1 squared is 0. Okay, so that's what we're up to. What we want to do is just we're going to, so our strategy is going to be the following. We're going to construct q1 cohomology, and then we're going to show that q cohomology is actually isomorphic to q1 cohomology. Okay, and thereby construct q cohomology. So the first part of the problem is not it's a huge simplification over q cohomology because q1 is a very simple operator. In particular, it's quadratic. So q1 cohomology quite. I mean, maybe you guys should try just using the oscillator definition. Just directly construct the cohomology. Construct states in its cohomology. What we're going to do is to give an abstract argument. But q1 is simple enough that you could just directly sit down and construct its cohomology by hand. Okay? But I'm going to work a little abstract. The abstracting is useful because it will help us in generalization of q cohomology. Okay, so how do we proceed? The first thing I do is to define an operator R, which I just pull out of a hat. I define my operator R to be 1 over k plus, and then replace alpha minuses by alpha pluses and c minuses by b minuses. So sum over b minus n, alpha minus n, 1. Okay? This is my definition of this new operator R, and you're thinking, my God, this is going crazy, definitions upon definitions. We're almost near the end of the definitions. We're going to get to the point. Okay, so hang on. Now the next thing we do is to compute the anti-commutator of Q1 and phi. Okay, so let's do this little computation. First thing is a k plus, which cancels to 1 over k plus, so that doesn't enter. So what we want to do is to compute the anti-commutator of C minus M alpha minus M and anti-commutator with B minus K, let's call it, alpha plus K. Everything summed over from overall non-zero values of M and K. Say again? Alpha plus, thank you. Yes. If this was alpha plus, I wanted to be the answer. Thank you. Okay. So now what are we going to get? So let's be, the only thing to be careful about is signs. Okay? Either you can remember some abstract rules in doing anti-commutators, or you just work it out by pulling things through. So let's work it out, by pulling things through. Okay, so let's look at Q1R. That is equal to sum over m, sum over k, c minus m, alpha minus m, b minus k, alpha plus k. Now let's pull this alpha minus m through this guy. Okay, here you pull this through free, and in pulling this through, you get a factor of you just force m to be minus k. Okay, so this is equal. This thing is equal to a term when you pull it through, which is sum over c minus m, b minus k, alpha plus k, alpha minus m, plus the term that you get from the commutator, which is sum over okay, now this term has two parts. It depends on whether m is positive or negative. Because we have alpha,
It will always be delta.
it will always be delta with a factor of 1 over m. Where is my 1 over m? With a factor of m, yes. Yeah. So we'll just keep the factors there. So let's do it. So this thing is plus m times c minus m, b minus k, times delta of m is equal to minus k. So let's set this guy to be equal to m. Okay? Now the next thing we want to do is to pull this guy through this guy. Okay? So we will also get, in doing that, so we get, this is equal to R times Q1, that's what we get once we pull this guy through. Okay? Plus this, plus whatever we get from this computation relation.
Minus atoms.
Is equal to minus R times Q1, which is what we wanted. Thank you. Q1. Okay? So we get so we have that Q commutator R is equal to this guy, anti-commutator R is equal to this guy, plus what we get pulling this through.
The anti-commutator
Of this C minus M and B minus K. Okay. Now that guy simply gives you what? Now what are the commutation relations of C and B? So right. So we have that when this is positive, it basically depends on when this is whether the guy is positive or negative. Right? We had we want annihilation with creation is equal to 1. So remember what the anti-commutation relations C and B were. CM BN this is for the substitution. This is fermionic, so just is no, it's just one, right? Yeah. What are the factors of n? Sorry. sorry, I think that it's just, sorry, CMBN was simply delta of M minus N. It was just that. Okay, yeah, I think it was just that. Sorry. Okay, so now if we do that, we get an additional factor of this object here. We get an additional factor of this object here when K and M are equal. So let's write down the final answer. This is sum over M C minus M B M plus sum over M alpha plus M alpha minus M, alpha minus minus M. And everywhere M is not equal to 0. Okay. Now let's interpret the result. Okay. So what is this guy here? This guy is the number of plus oscillators weighted by its level plus the number of minus oscillators weighted by its level. Right? It's the term that doesn't have interpretation. Number of plus oscillators plus number of minus oscillators weighted by level. Okay? And this guy here is, so let's see, suppose M was positive, then we would have M was positive counts the number of C oscillators weighted by level. You see that? Because if you have a C oscillator, B will destroy it with factor 1, replace it with this with a factor M. On the other hand, if M was negative, okay, we get a minus from here, we get a minus from the fact that we have to flip this in order to first destroy. So M negative counts the number of C oscillators weighted by level. Okay? So this quantity, this Q1 commutator R, is simply equal to number of C oscillators plus number of B oscillators, let me call this bit, weighted by level. Number weighted by the energy level. Plus number of plus oscillators weighted by level plus number of minus oscillators weighted by level.
What you get, by definition, the minus of N minus W is minus M alpha plus minus M alpha minus. Okay, how is N minus defined?
N minus W is defined as N minus W is equal to sum over M greater than 0, so M is equal to 1 to infinity of alpha plus M alpha minus minus. It's the thing that counts the number of minus oscillators weighted by that. Okay? N plus W is equal to sum over M is equal to 1 to infinity alpha plus minus M alpha minus M. Okay? NWC is equal to sum over M. M is equal to 1 to infinity. Then C minus MBM. Okay? And NWB is equal to M is equal to 1 to infinity M B minus M CM. Is this clear? I'm taking each of these two terms and broken up into the parts where M is positive, the parts where M is negative.
Alpha minus seems to have gone on the other side.
Which sorry, say
so N minus, the alpha minus has come.
Which side? These things. Oh, you're worrying about the normal ordering. Yeah, okay, good. Yeah, okay. Well, good. So one should work out the normal ordering independently. Okay, so you're completely right. This calculation was modulo ordering. Okay? Now, we have to independently work out, I'm claiming the right answer is actually when you write it this way. How do you know that? You know that because both Q and R annihilate the vacuum. In order to, you see, what was this thing? The easiest way to fix normal ordering constants, okay, when something is defined by a commutator, is if you know individually what the elements of what each of the two guys do to a particular state. Okay, so now let's so it's a good question. Let's remind ourselves about the definitions of Q and R.
I just want to know whether I'm understanding this right. So what we are doing is that there will be a normal ordering constant which will arise from the X oscillator, the plus minus oscillator, which is exactly cancelled by the DC oscillator.
It will be exactly cancelled. It's sometimes hard to keep track of these normal ordering because they're infinite.
Yeah, but term by term.
Term by term, if you allow yourself to think that way, that's what will happen. But that's dangerous. That's dangerous because infinity minus infinity could be anything. Okay? So it's much safer to work, in some consistent way. So the way we would actually do it, really, one way to do it is by looking at the current corresponding to these operators, computing OPEs and so on. Okay? But there's another way that you could work, which is also safe, it's completely correct. And that way is this. See, the operator in question is being defined. Okay, the operator in question is being defined by the anti-commutator between two operators. Okay, the only ambiguity we have in the question is about we have to put operator up to a constant. So let's just say that we know what we've got up to an unknown constant. Okay, and determine this constant by seeing what the action of the original operators was on a particular state. Now I'm claiming that both the original operators Q1 and R annihilate the vacuum. Therefore, it must be true that anti-commutator of Q1 and R annihilates the vacuum. This form of the operator does annihilate the vacuum because I've normal ordered it. Okay? So all I have to do to convince you that this is the correct answer is to demonstrate that both Q and R annihilate the vacuum. Okay? Let's remember what Q1 and R is. Q1 was equal to K plus times sum over M alpha minus of MC minus M. Okay? It's totally clear. Basically, it's one positive mode, one negative mode. Therefore, one of the two states always annihilates the vacuum. Since the sum runs over M not equal to 0, the sum runs over M not equal to 0, you don't get any possible contributions from 0 nodes. Okay? Similarly with R. R was equal to 1 over K plus sum over M not equal to 0 alpha plus M B minus M. The sum runs over M not equal to 0. In this case, even if it had run over M equal to 0, B0 would have annihilated the state. We don't even have to invoke that. Sum runs over M not equal to 0, then the state annihilates the vacuum. So there's always one destruction operating. Okay? Therefore, anti-commutator of Q1 and R must also annihilate the vacuum. So we've done the calculation that finally fixed the normal ordering constant by normal ordering the final ones. Is this clear? Yes, it's unambiguously determines the answer. That's a good question. Thank you. Okay. So now let's focus on this option. The first thing that we see is that the right-hand side here is positive definite. Okay, the entire Hilbert space of the string oscillator construction can be decomposed into eigenvalues to the right-hand side, but there's a zero eigenvalue. That's the state with no plus, no minus, no B, no C oscillators, and then there are positive eigenvalues. Okay, now Q1 commutes with this thing with that given name. We'll call it S. Okay? So now I claim that Q1 commutes with S. Or more precisely, attributes with S. Why is this the case? Well, Q1 has terms with either one creation operator of minus and one annihilation operator of B, or vice versa. Always has a mode in which one state is being created, the other state being annihilated. This thing democratically counts the number of all states. So since one is being created, the other is being annihilated, the state that is created is equal in level to the state that's annihilated. It doesn't change the quantum number of S. Okay? So we can, instead of considering the problem of Q1 cohomology, we can discuss the problem of Q1 cohomology separately in every eigenvalue of S. Right? Because if S psi is equal to A psi, then Q1 on then S of Q1 on psi is equal to A on is equal to Q1 on S of psi is equal to A times Q1 of psi. So you've got a state that has eigenvalue A under the operator S acting with Q1 and it maintains that eigenvalue. So the whole problem of cohomology splits up into block by block problems, one for each value of the eigenvalue. Well, you want a minus.
No, okay, our problem. No, actually, Q1 should commute with S. We should commutated of Q1 and S. S is a bosonic object.
S is a bosonic. Yeah, S is a. Oh, thank you. Thank you. Right. Okay. Now the next important claim is that Q1 cohomology is empty if A is not equal to 0. In all sectors of S eigenspace with non-zero eigenvalue, Q1 cohomology is empty. Now this is an argument that appears again and again in our kind of physics. It was the argument Witten used in the study of the Witten index. It appears again and again in the study of supersymmetry. But it's good to look at this argument. It's a very simple argument, but it sort of seems tricky at first sight. So, okay. Well, what I want to claim that in some sector in which S has non-zero eigenvalue A, Q1 cohomology is empty. By the way, in order to prove that, I will prove that if Q on a state psi is equal to 0, then it is also Q exact. Okay, so consider any state psi such that S on psi is equal to A on psi and A is not equal to 6. Okay? Now, the fact that S on psi is equal to A on psi is the fact that Q1 times R plus R times Q1 on psi is equal to A psi. But Q annihilates the state by assumption. Therefore, we get Q1 on R psi is equal to A psi. Again, by assumption A is not equal to 0, therefore we've got an equation for psi. For psi is equal to 1 over A Q1 on R psi. Which tells us that if psi is not equal to 0, of course there's a possibility that psi was 0, in which case you would have R annihilating psi. So psi is not equal to 0, R psi is not equal to 0, so otherwise this equation would be satisfiable. Okay? So what you have is that this state is Q1 on some non-zero state, and therefore it's Q1 exact. Okay? It's a very simple argument. It arises when discussing the representation theory of supersymmetry. Because when you look at supersymmetry in flat space, you have Q dagger is equal to H. And QH is 0. So it's the same kind of argument that says that states of non-zero H appear in pairs. Okay, it's that kind of thing that appears again and again in various contexts. Okay, so but now focusing just on this in the study at hand. Okay, what have we shown? We've shown that if you have a state with non-zero value of this eigenvalue, okay, then and it is annihilated by Q, then it's also Q exact. Fantastic. That means that there is no state in the cohomology. There is no state in the cohomology of Q1 with non-zero eigenvalue of S. Therefore, all states in the cohomology of Q1 have zero eigenvalue of S. But what was the eigenvalue of S? Remember, eigenvalue of S was number of oscillators of plus number of oscillators of minus plus number of oscillators of B plus number of oscillators of C. Each of these terms is individually positive definite. The only way you get zero is for all of these to be zero. So we've demonstrated that Q1 cohomology lies entirely within. Q1 cohomology lies entirely within the cohomology of the Lytle cohomology we were discussing before. Namely, the cohomology of states created only by transverse oscillators of the string. We still want to demonstrate that Q1 cohomology is equal to this. We have to show that every state with S equals 0 lies in Q1 cohomology. Okay? So that's what we're going to do next. But we've already achieved a large part of our job, though only for Q1, not for Q2. Yes?
We have to show that this is about
to Q cohomology, which will come. Okay. Now, the next thing we're going to do is to show that Q1 annihilates all states with S equals 0. Okay? Q1 annihilates all states with S equals 0. This demonstrates that Q1, that all of S equals 0 is in Q1 cohomology. Because if a state were to be Q1 exact and have S equals 0, since Q1 commutes with S, it must be Q acting on some state with S equals 0. Is that clear? You see? Well, let me say this. See, suppose we have there existed an exact state with eigenvalue of S equals 0. Then this state is Q1 acting on some state. But since the eigenvalue of the final state is 0 and Q1 commutes with the operator S, the eigenvalue of the state that we were acting on to produce this exact state must also have been 0. Okay? So if we can show that Q1 annihilates all states with S equals 0, we would have in one shot shown two things. A, that all states with S equals 0 are Q1 closed. And B, that there is no exact state with S equals 0. Because had there been an exact state with S equals 0, it would have required Q1 to not annihilate some state with S equals 0. Is this clear? Okay? So, if we can show that Q1 annihilates all states with S equals 0, we're through. Then we have demonstrated that Q1 cohomology is the Lytle cohomology. So let's first actually, I'm going to do it more abstractly because of the generalization. But first let's actually look at the definition. Once we look at by looking at the definition, it's obvious. Okay, the definition, remember, was K plus C minus M alpha minus M. But states with S equals 0 have no C oscillators, no B oscillators, no alpha plus oscillators, no alpha minus oscillators. Since each of these things always include a destruction operator, it commutes through all the other oscillators present and reaches 0. Okay? So it's clear that Q1 annihilates all the states with S equals 0 just by construction. But now I'm going to give you a slightly more abstract argument. A slightly more abstract argument for this phenomenon. The argument starts by noting that S commutative Q1 is equal to 0. Okay? So, this means that SQ1 is equal to Q1S. Now, suppose there was a state that was annihilated. Suppose there was a state that was that had S equals 0 and was annihilated by 2. Okay? So, and was not annihilated by Q1. That's what we want to show. Right? There's no state that is not annihilated by Q1. So, suppose there was a state that was not annihilated by Q1 and had S equals 0. So, let's say that that state is psi. Okay? So, let's act with Q1S on psi. So, Q1S on psi is equal to 0 because S is equal to 0 on that state. But by flipping the order, we get S on Q1 psi is equal to 0. That's a perfectly possible equation. Well, there are two ways in which it could work. It could work that Q1 on psi was 0, or it could work that Q1 on psi was not 0, but S on Q1 psi was 0. We're assuming that it's working the second way. That Q1 on psi is not equal to 0, and checking to see if there's a contribution. Okay. But, you see, the point is that Q1 is an operator with ghost number 1. Okay? Remember what ghost number was? Ghost number was number of C's minus number of B's. Okay? Okay. Now see, psi had S equals 0, therefore had number of B oscillators and C oscillators both equal to 0. Since Q1 has ghost number 1, Q1 psi can't have number of B oscillators and C oscillators equal to 0. What the number of B oscillators is and what the number of C oscillators is, we can't say. But the difference between them is 1, so each of them can't be 0. Is this clear? So Q1 psi, okay, is some state which has S equal some non-zero value. It's a decomposition of states with non-zero values of S. But the kernel of S with non-zero eigenvalues of S is 0. There's no state with non-zero eigenvalues of S, of course, for which S on that state is equal to 0. Therefore, while this equation must be true, the only way it could be true is if Q1 on psi is equal to 0. If we assume that Q1 on psi was not equal to 0, we would find a 0 mode of S, but we have an independent argument that the eigenvalue of S is not 0. So this is a contradiction. Is this clear? Okay? So, we have an argument by direct examination of the operator, but there's a more subtle, it's an obvious argument, but it's a little difficult to state. But we just said it. Just abstractly, from consideration of the ghost number of Q1, okay, that it's impossible that Q1 on psi be anything but 0. If psi has eigenvalue 0 under S. Okay? Now I'm giving you these more abstract arguments each time because while with this explicit operator Q1 we can just do everything by hand, now, as we do the generalization now to Q, we can't do everything by hand anymore. Yet these abstract arguments can work. Okay, so is everyone? So we've completed our discussion of Q1 cohomology. We've concluded that Q1 cohomology is identical to the light cone. By the way, identical in a very explicit sense. Our construction of the cohomology, was really, excite only the transverse oscillators. So in particular, we have shown that the Hilbert space is identical to the light cone, and the inner products on this Hilbert space are identical to the inner products on the light cone space. So in particular, we've shown that within the Q cohomology there are no negative or zero norm states. Okay, the matrix of inner products is positive definite within Q cohomology. This is far from obvious. Because the full Hilbert space with 28 oscillators and many zero norm and negative norm states, as we will see as we consider examples. But if we restrict just to Q cohomology, the Q1 cohomology, we're sure this. Now we have to check what happens with Q cohomology. But before that, any questions or comments about Q1 cohomology? Okay, unless I get a question, I'm going on. Fine.
Can you restate the argument?
For what?
Of y or
this one?
Yeah. Y or Q's. S equal to 0 states are not.
You want this argument or the earlier thing that I said only in words?
Yeah, y is S equal to 0 states. Why they can't be exact?
Okay. So that argument goes in two steps. First, we've shown that every S equals 0 state is annihilated by Q1. Okay? Therefore, in particular, every S equals 0 state is Q1 closed.
Okay,
fine. That's fine. Now, suppose there was an S equals 0 state that was Q1 on chi. Let's look at what the eigenvalue of chi must be under S. What must it be? If psi is Q1 and chi, psi has S equals 0, what must chi have?
Q1 has
0 charge at S.
0 charge at S. And
therefore chi has S equals 0. Okay? So, then there must be, if psi is Q1 on chi, it must be Q1 on chi, where chi has S equals 0.
Yes.
So we've shown that there's no state chi with S equals 0 that is not annihilated by Q1.
Okay.
So it's impossible that psi is equal to Q1. Clear? Okay. Okay? So now let's move on. Now, this was a fun game to understand Q1 cohomology, but we want to understand Q cohomology, not Q1 cohomology. How do we do that? Well, the trick is to continue to use the operator R, but to replace the operator S by what you get by Q commutator. Let's consider the operator Q commutator. So remember, what was Q? Q was Q minus 1 plus Q0 plus Q1 commutator. Now let's see. Let's remind ourselves. Okay? Let's remind ourselves what the value of R was under NLC. Remember the original NLC operator that we looked at, we've forgotten over the last 30 minutes. The number of minus oscillators minus the number of plus oscillators. Okay? Remember Q1 had charge 1 under NLC, but R had charge minus 1 under NLC. Because we replaced minuses with pluses. So R has charge -1 under NLC. Q1 has charge 1, but by the subscript indication, we call R -1 Q1. But anyway, the subscript gives you the charge under NLC. So Q0 with R has charge has charge -1, and Q -1 with R has charge -2. So this thing is going to be equal to S, our good friend, this has Q1 commutator, plus U. But we're not going to say what U is, we're not going to work out U in detail. The only thing about U that people keep track of is its charge under NLC, and U has negative charge. Under NLC. Okay. Okay. So now consider the following. Consider any state psi 0. Consider any state psi 0. Okay. Consider any state psi 0 that is annihilated by S. Such that S and psi 0 is equal to 0. Okay. That is, as we have demonstrated, consider any state psi 0 that is in Q1 cohomology. Now, I want to give you a construction of a state that is in S plus U, that is annihilated by S plus U. See, essentially what we're using is the fact that the kernel of a lower triangular matrix is equal to the kernel of the diagonal elements of the matrix. But I'll prove it to you exactly. Okay? So, what I want to do is to show that there is a one-to-one map. By explicit construction, I will construct a one-to-one map that takes states in the kernel of S and produces states in the kernel of S plus U. Okay? So how do we do this? Well, you see, let me give you the construction, let me try to understand it. The construction is, consider psi, which is equal to 1 minus S inverse U plus S inverse U acting inside. Now, whenever you see a construction involving S inverse, you should scream. You should scream and say, what do you mean S inverse? Because S has a space with 0 eigenvalues. However, remember that U has NLC, which is negative. Okay? So U on psi has non-zero eigenvalue of S. Because if NLC is negative, it means the number of minus oscillators minus the number of plus oscillators is negative, which means in particular the number of plus oscillators and number of minus oscillators can't be 0. Okay, so either U, suppose we add U on psi, okay, remember that psi 0 had S equals 0. Psi 0 had S equals 0. So let's count the NL. Let's look at what S can be for U on psi 0. Okay, psi 0 had S equals 0, therefore NLC equals 0. So NLC of U on psi is some negative number. Therefore, U on psi is some state with number of minus oscillators minus number of plus oscillators being some negative number. In particular, it's impossible the number of minus oscillators and number of plus oscillators is both 0. Therefore, it's impossible that this state has eigenvalue 0 under S. So S inverse, while it doesn't make sense on all of the inverse space, makes sense when you put a parity with the U in front. Okay? And now that this is annihilated by S plus U is obvious. It's obvious, for instance, where you can write out the series if you want, or it's obvious algebraically because you can write this as. So what is this? This is 1 over 1 plus S inverse U. Okay, so that's 1 plus S inverse U. So that you can write as write that. Yeah, but it's coming from right, but because it's the inverse, it goes to the left. So it's right. So this is 1 plus S inverse U inverse. Okay, which is the same thing as S plus U inverse S. Okay, and then when you add it with an S plus U, is that, and you get S on psi 0, which will be 0. What I'm saying here is that this thing is equal to S inverse times S plus U inverse, the whole thing inverse, and then that is right. Yeah, that's an algebraic manipulation, but otherwise you just look at term by term.
Why shouldn't we be worried about whether S plus U is significant?
Yeah, that you should be worried. That's why I used to way that why are we going to use S plus U? This is just an algebraic way of understanding why we get 0. That the action is well defined is clear from this form. But now this algebra will ensure that you will get 0. Okay? If you don't trust this manipulation, you can just multiply. Let's say you get cancellation term by term. Right? You can see this. The first time U multiplies this, S multiplies this, U minus U. Then you get U squared. So it's just term by term cancellation. Is this clear? Fine. So we've concluded that there is a one-to-one map. There is a one-to-one map between, well, for any state in S cohomology, we produce a state in S plus U cohomology. Not cohomology. In any state of the kernel of S, we produce a state in the kernel of S plus U. Okay? And now, abstract arguments. All the abstract arguments that we used before continue to hold. Let's repeat them. Remember that Q commutator of R was equal to S plus U. Okay? So, firstly it follows, by the same argument we used before, that any state with non-zero value eigenvalue of S plus U